Let's remember that permutations mean we're trying to figure out how many different options, how many different ways we can order a certain number of things. And in this case, we're going to talk about permutations without repetition. These are pretty much just standard permutations. When people say permutation, this is usually what they mean. And remember, order matters with permutations. So 3, 2, 1 is different than 1, 2, 3. So let's talk about a running example. So say you have 10 people running a race, and you want to figure out how many different ways you can have a first, second, and third place winners. Now, this is a permutation, not a combination, because first, second, and third is different than third, second, first. Meaning, if I come in first and you come in second and Mrs. Abrams comes in third, that's different than if she comes in first, you come in second, and I come in third. Okay, so this is a permutation, not a combination, because it matters. It's a different order if we pick me in first or me in third. Even if it's the same 3 people, if we're switched or moved around at all, it's a totally different order. So that's a permutation. And it's without repetition because I can't be in first and second, right? I can only get either first or second. And once, say, I get first place, then I'm out of the running for second place, right? They can't choose me as the second place winner. So let's figure out how we do this with actual math. Okay, so we figured out with the fundamental counting principle that all we have to do is we take the number of things that we have and we multiply it. So, if you had 10 people and you were saying if you could repeat, it would just be 10 times 10 times 10, right? It would just be, well, I can pick from 10 people the first time and 10 people the second time, 10 people the third time. But in our case, you can't pick from 10 people each time. You can pick 10 people the first time. So as you are picking first, second, and third, the first person for first, you have 10 different people it could possibly be, right? And again, we could draw a tree diagram. Here's the person handing out the medals. Okay, and they have 10 different people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different people that they could pick to give that medal to for first place, right? But then what happens? Then what happens is that one of those people gets first place, and the next time we can't pick them for second place, right? So the second time we only have 9 people. 1, 2, 3, 4, 5, 6. See, I can't talk and count at the same time. We only have 9 people that we could choose for second place. Okay, so the first time we have 10 people. I need to write this over here so we have room. And the second time we only have 9 people that we can pick from because the first person's already been picked, right? Without replacement. Then for third place, how many people do we have left? Well, 2 people have already been picked for first and second. So now, say off of this one, we'd have 8. We'd have 8 people here. So how many different ways can we pick a first, second, and third place winner from 3 people? From 10 people. Oh gosh, from 10 people. Well, that would be 10 times 9 times 8, which would be 720. There'd be 720 different ways that we could pick a first, second, and third place winner out of 10 people. Let's do another example. So we have 16 different pool balls. They have numbers 1 through 16, and we want to figure out how many different ways could we order them, right? So like we're going to reach in to like a bag with all of these balls in it. We're going to pull one out and we're going to set it down. And then we're going to reach in and pick another one and set it down. So we have like an order, maybe this is ball 3, 5, 1, 7, 10, so on. We're going to put them in order. We're going to figure out how we can do that. So the first time, if I have them all like in a big cloth bag and I'm going to reach in and grab one out, how many different options could I possibly pull out? Well, I could possibly pick 16 different options, right? And then once I've pulled that out and set it on the pool table and I reach back in, how many options do I have now? Well, I have 15 options now, right? And I set that on the pool table and I reach back in and now I have 14 options. And then I only have 13 options, then I have 12, and then I have 11, and I have 10, then I have, and so on and so forth. It goes all the way down to 1 till I have only 1 option left to pick out. So I would use this idea behind the fundamental counting principle to multiply each of these numbers together to figure out how many different ways could I set these pool balls in order. Well, in the end, let's see, this is millions, billions, trillions. In the end, I have 20,922,789,888,000 different ways that I could potentially pick out those 16 balls and put them in place. Isn't that crazy? That's insane to think about. But that's how many different permutations, I almost said combinations, but it's not. That's how many different permutations we could get. But what if we don't want to pick all 16 of them? What if we're just trying to pick 3? And this is also an example. We're talking about pool balls, but this could be like lottery numbers, right? There's a bunch of lottery numbers. You pick one out, set it down. You pick another one out, set it down. And we're going to just pick 3 of them out. Okay, so how many different options do we have? Well, again, the first time I pull out one, I have 16 options. The second time I pull out one, I have 15 options. The third time I pull out one, I have 14 options. So if I have 16 different pool balls and I'm going to pick 3 of them, then there are 3,360 different ways that I could possibly pick those out in order.